we're going to uh, start with the next slide for chapter 3, chemical bonding. It will be on resonance structure concept. So as we calculate based on the equation given previously, following to the equation of n minus a equal to s. And then if you are given a structure of SO3, and then you can have the value of n, value of a, value of s, and value of a minus s. So from that, you then rearrange which atom will be the central atom and which atom will be the outer atom. So for this case, S will be the central atom, and we have another 3 oxygen surround the sulfur atom. So by adding the electron to the structure, we finally will have the Lewis structure as the example in the slide, and also the dash formula like this. So this will be the dash structure. So you can see here the double bond occur in one of the bond. So we have one double bond of SO. However, the SO the SO bond that occur here can also occur on the second SO bond and the third SO bond. So in this case, the resonance structure might take place. So there is 3 possible structure of SO3. Okay, so this is the first one, and second one, just differentiate by the location of the double bond, and finally the third structure. So the double bond can be placed in one of these 3 places. So when 2 or more Lewis formula are necessary to show the bonding in a molecule, we must use equivalent resonance structure to show the molecule structure. So this will be the reversible arrow to show the resonance structure. So the double-headed arrow are used to indicate the resonance formula. So as the resonance is flawed method of representing the molecule, meaning that there are no single or double bond in SO3. So the write-up of SO3, for example, like this, is just to easily explain the structure of SO3. However, since the electron can be delocalized within the bonding, so in fact, all of the bond in SO3 are equivalent. So the best Lewis formula of SO3 can be drawn as this one. So meaning that the delocalization of electron can occur to the all SO bonding. So same goes if we have oxygen, for example. So oxygen can, ozone can be represented either by this structure, or we can have another one like this. Okay, so either you may draw it using single and double bond drawing, or you may draw it as, and then there is a present of dash dot bonding. So this is to represent that the electron can be delocalized, between each bonding. Okay. However, in drawing the chemical bonding, there is some octet rule exception. So some bonding might not following the octet rules. So this one, there are some molecules that violate the octet rule. For this molecule, the n minus a equal to s does not apply. So there is 5 category of this exception. The first one, the covalent compound of beryllium. The second one, the covalent compound of the group 3. The third one, species which contain an odd number of electrons. The fourth one, species in which the central element must have a share of more than 8 valent electrons to accommodate all the substituent. And fifth, compound of the D and F transition metals. Okay, we look some example. Okay, before that, in those cases where the octet rule does not apply, the substituent attached to the central atom nearly always attain a noble gas configuration, and the central atom does not have a noble gas configuration, but may have fewer than 8 electrons. And that for exception 1, 2, and 3, it will have fewer than 8 electrons. Supposedly, it need to have 8 electrons to achieve the octet. But then, some of them may not have 8. And then, the second case, the central atom have more than 8 electrons. This will be on the exception 4 and 5. Supposed to have 8, but it exceeding 8. Okay, we have some example here. Okay, for exception number 2, for boron tribromide, BBr3. So boron, for group 3, we have 3 electron on the valence shell, and for bromine, we have 7 electron on the valence shell. So as the formula of BBr3, as the boron only have 3 electrons that can be used to share or what we call can be used on the bonding, then only 3 bonds that will form. So we can draw it like this. So 3 electrons that originating from boron, and then 1 electron from bromine. So this one will be used for the bond formation. Since 1 electron need to be shared between bromine and boron, then only it will form the bond. Okay, so in this case, boron will only have 6 electrons. So 1, 2, 3, 4, 5, 6. Instead of having 8 electrons, boron will only have 6 electrons. That's violating the octet rule. Okay, so for bromine, it is clear. Bromine will have 8 electrons. Okay, so that will be the example for exception number 2.
Masa lecturer aku ni suka sangat benda aku? Tak faham lah aku.
Macam mana tu?
Dia suka aku buat. Tiba main Syairah.
Mungkin lupa mute tu.
Ada masuk.
Okay, the second example, we have a ASF5. Okay, so this is for group 5, nitrogen family. So for AS, it will have 5 electrons on the valence shell, right? So for fluorine, it will have 7. So in this case, for AS, let's say we put the electron here. So 5 electron from AS, and then we have individually 1 electron that coming from fluorine. So in this case, it makes AS to have 10 electron, not 8. Right? So this already violating the octet rule. Okay. But then this structure occur, but then we then consider that five uh, item or particular that violating the octet rule. Okay, now we complete all the discussion on bondings. So we already discussing that we have the ionic and covalent compound. Ionic meaning that mixture or bonding that form between non-metal and metal, and for covalent compound is non-metal with non-metal. So as general comparison, the melting point for ionic compound, for melting point comparison, the ionic compound are usually solid. So as uh, an easy example, we have sodium chloride. This is an ionic compound, meaning that sodium is metal, chlorine is non-metal. Okay, so for this one, or as a general for ionic compound, it is usually solid with high melting point. So typically more than 400 degrees C. So for covalent compound, it is typically either gaseous, liquid, or solid with low melting point. It depends on type of covalent compound. Okay, so for example, we have let's say we have nitrogen dioxide or carbon dioxide or water molecule. So these two are gases and H2O is liquid. So for covalent compound is typically having a lower melting point, less than 300 degrees C, depend on the compound itself. The second comparison on the solubility in polar solvent, we already discussed that polar solvent, meaning that it have some polarity, meaning that there will be a different region of delta positive and delta negative that make it polar. So for ionic compound, it's generally soluble in polar solvent, and for covalent compound, it is generally insoluble. So we take an example. Let's say we have, again, we use sodium chloride. So this is an ionic compound. And let's say we have water molecule. Since in water, we have bonding of HOH, and the electron density will be on oxygen. So this will be more, sorry, this is negative, more negative, and hydrogen will be more positive. So polarization took place in water. So sodium chloride will easily dissolve in water. So for covalent compound, let's say we have what to take. Let's say we have hexane. Hexane is a covalent compound. 1, 2, 3, 4, 5, 6. Hexane. Hexane will not dissolve in water. So it will form a layer. Let's say we have two layers of hexane, and water depend on their density. So in this case, water will be on top, and covalent compound or the hexane will be the bottom. Okay. Next is solubility in non-polar solvent. So non-polar solvent, again, we can use hexane or heptane and so on. So this is 1, 2, 3, 4, 5. So this is heptane. There is no polarity, meaning that it is non-polar solvent. Ionic compounds are generally insoluble. So sodium chloride will not dissolve in heptane. But then, let's say we have uh, pentane, five, uh, five carbon ring. So it is dissolved in a non-polar solvent. So it is like a general of uh, like dissolve light. So So polar component will dissolve polar molecule, non-polar component will dissolve in non-polar molecule. Next is the conductivity in molten, solid, and liquid. So ionic compounds are generally conduct electricity since they contain mobile ion. So take another example of sodium hydroxide. Sodium hydroxide is a solid form. It is ionic compound. When we dissolve it or we heat it at high temperature, it will turn from solid to liquid. So in liquid stage, there will be formation of Na plus and OH minus. So this ion formation will be electrically conductive. So covalent compound generally do not conduct electricity because there will be no free ion form in the molten stage. Molten meaning that it will be heated at high temperature and turn into, for example, of sodium hydroxide from solid into liquid. Okay, conductivity in aqueous solution. Aqueous solution meaning that water molecule. Okay, so ionic compound generally conduct electricity when it is dissolved in water since it contains the mobile ion similar to the molten condition, and non-covalent compound are poor conductors of electricity. So to make it easy, ionic compound will conduct electricity, non-covalent covalent compound will not conduct electricity. Next will be on the formation of compound. Ionic compound are formed between elements with large difference in electronegativity. So that's why it happened or took place between non-metal and metal. Since metal will be having lower electronegativity and non-metal will contain the relatively higher conductivity. So let's say we have sodium fluoride. Sodium will be on the group 1, fluorine will be in group 7. It will, sorry, group 17. It is apart away between group 1 and group 17, and that's typically ionic compound formation. And for covalent compound are formed between elements with similar electronegativity. So let's say we have what we call uh, again we use butane C4H10. Okay, so formation of CC bond will be on the similar electronegativity and usually involving a non-metal with non-metal. Since hydrogen also is a non-metal, it's a gas. Okay, on the hybridization of atomic orbital, we will skip this part and we move to the forces that took place in the molecule. So we will discuss on intermolecular forces and metallic bond. So in intermolecular forces, it is a attractive force between molecules, and there is another force which is intramolecular forces. This is whole atom to go together in molecule. So how do we compare the intermolecular forces and intramolecular forces? Okay, so generally, intermolecular forces are much weaker than intramolecular forces. So let's say we have an example of 1 mole of water. Uh, it required 41 kilojoule of energy to vaporize 1 mole of water. So this is intermolecular forces, and it will require 930 kilojoule of energy to break all OH bond in 1 mole of water. Okay, so let's take this example. So let's say we have what HOH. Okay, since in water there will be a hydrogen bonding that make water in liquid condition. So the energy that required to break water molecule, each water molecule will be the intermolecular forces to form individual water molecule. This will be in gas phase. So that's why uh, the energy required will be relatively low. So from liquid to gas, it will require to break one bond. This bond is called as intermolecular forces. However, to break all OH bond, so meaning that if we want to break the intra bonding and remove the OH molecule, it required a higher energy. Okay, so that's the difference between inter and intramolecular forces. So how do we measure or the output from these forces? We can see it from the boiling point, melting point, and also delta H of vaporization. Okay, that's on the first force. The second one is on the dipole-dipole force. So dipole-dipole occur between polar molecule. Okay, so let's say we have, let's take this kind of example. An organic compound in which there will be extra electron in oxygen, making it delta negative, and making carbon that attached to the C double bond O will be delta positive. Now, for dipole-dipole, it will attract uh, to the opposite charge, since for the first oxygen here, it is delta negative. It will attract it to the uh, element or compound that having the delta positive charge, so that it will have a balance or a near to neutral charge. So that's why interaction will take place between opposite charges. Okay, so this will be the orientation. If we draw it on the positive and negative charges on the molecule, or we can draw it straight away on the molecule itself. And we need to identify which one will be the delta negative side and which one will be the delta positive side. So then we can have some idea the dipole-dipole interaction between molecules. Okay. Since this one is dipole-dipole, we have another one, ion dipole force. So this will be the attractive force between an ion and polar molecule. The first one is attractive force between polar molecule. So the second one is ion and polar molecule. So let's say we dissolve, in this case, sodium iodide, right? When we dissolve it in water, water will have the polarization. So this will be, oxygen will be more delta negative since it contain more electron density on oxygen, and hydrogen will be more delta positive. Dissociation of sodium iodide will form sodium plus and iodide, iodide ion I negative. So the Na plus will easily attract to the oxygen side of water, whereas the iodide will easily attracted to the hydrogen side of water. So it is to show that when we put sodium iodide in water and it is dissolved, so sodium ion will go to the oxygen area, whereas the iodide will go to the hydrogen area. So this will be the ion dipole forces. Next will be dispersion force, or we call it as London force. For London force, it is an attractive force that rises as a result of temporary dipole induced in atom or molecule. So let's say we have an atom of molecule that having no charge. So this example showing that it is neutral. The neutral, sorry, this is neutral compound. So this neutral compound can be induced or to have polarization that only occur as temporary. So let's say we have a cation, or let's say we put it calcium 2 plus. Since calcium having positive charge, interaction with the neutral compound will make some part of the compound is negatively charged and another part of it will be positively charged, right? But then this is only occur temporarily. It's not a permanent charge. So this is for ion. uh, the next one, if we have a polar molecule or polar compound. Since in polar compound, it's already contain polar, means the delta positive region and delta positive region. So it will also induce the neutral compound to have a negative or positive region from its neutral condition. Again, need to remember that this only happen temporary and not permanent. Okay. The polarizability of the is with which electron distribute in the atom or molecule can be distorted. So we can have an idea the polarizability of the molecule. So the polarizability increase with a greater number of electron. The higher number of electron will give higher polarization or polarizability and more diffuse electron cloud. So the dispersion force usually increase with the molar mass. So semakin bertambah or increase the molar mass, the polarization will be increased. So we have example of methane. Then we have here carbon tetrafluoride, carbon tetrachloride, carbon tetrabromide, and chlorine gas. This is Cl4 tetrachloride. So in this case, what happened is that we have, sorry, this is carbon tetraiodide, Ci4, not Cl. So we can see here for methane, methane will have a melting point of 100, negative 182.5 degrees C. And then when we have carbon tetrafluoride, uh, the melting point reduced to negative 150. And then these 2 points, the greater number of electron. From fluorine to chlorine, the number of electron will be increased. The second one, there will be additional of electron cloud. Since from fluorine to chlorine, there will be another n. So meaning that additional of quantum number, it will include also the electron cloud around the chlorine atom. So for bromine also the same case, there will be another electron cloud, and for iodide even bigger. and comprising more electrons and also electron cloud. That's why you can see the melting point is increased from methane to carbon tetraiodide. Okay. So this supposed to ask you the type of intermolecular forces that exist between each molecule. If we have hydrogen bromide, HBr, hydrogen bromide is a polar molecule. So in polar molecule, it will have a dipole-dipole force, and also there will be a dispersion force between HBr molecule. For methane, the second example, for methane, methane is non-polar, then there will be no dipole-dipole force. It will only having dispersion force. The third one, sulfur dioxide. Sulfur dioxide also a polar molecule. It will have both dipole-dipole force and also dispersion force between SO2 molecules. So this is just an example. Let's say in your test later on, you will be asked type of molecule and to identify what is the forces that took place or occur in the molecule itself. Okay. So next is on hydrogen bond. So the hydrogen bond is a special dipole-dipole interaction uh, between the hydrogen atom in a polar NH, OH, or FH bond and electronegative oxygen, nitrogen, and or fluorine atom. So, so to make it short, it only involving nitrogen, oxygen, and fluorine. So that's why in water molecule, so let's take the first example, water molecule. We have HOH, and then there will be a hydrogen bonding. Hydrogen bonding is the most what we call um, the most difficult or required larger energy to break it. So this will be the hydrogen bonding that occur between oxygen atom with the adjacent hydrogen atom. Okay. In case of ammonia, for example, here we have NH3, and there will be a hydrogen bonding from nitrogen to hydrogen to the adjacent ammonia molecule. So anything that contain hydrogen and then can interact with the adjacent nitrogen, oxygen, or fluorine, it can form hydrogen bond. Okay, so another example, you may again look to the example given on your slide. Hydrogen bond also took place in alcohol. So let's say we have methanol, we have CH3OH. So this one can form hydrogen bond with the adjacent hydrogen. So let's say we have CH3OH. Right. So this is responsible to the uh, strong attraction between molecule and turn atom that supposed to be sorry, the molecule that's supposed to be logically at first place in gas phase into liquid phase. So due to the additional energy or bonding that took place between the molecule, it's already changed the structure, not structure, it's changed the appearance uh, of of the element itself. Why is the hydrogen bond considered a special dipole-dipole interaction? So it increase the boiling point of the molecule. So let's say we have water, hydrogen fluoride, ammonia, and methane. So let's take this one as example. Decreasing of molar mass will decrease in boiling point. So let's say we have oxygen, fluorine, and nitrogen in this case. So in oxygen group, when it's downing the group from oxygen to sulfur, selenium, and tellurium, it decrease the boiling point before it start to increase again a little bit. So the first element on each group will have higher boiling point. Okay, so the most important part is that you know the formation of hydrogen bonding between hydrogen in the molecule with the adjacent atom of oxygen, nitrogen, or fluorine on, and also you know to how to draw the hydrogen bond that happen on the structure. Okay, so I think that's it for chapter 3 on the chemical bonding.